Chapter 11, reactions of alcohols. We learned previously how to name alcohols, how to classify them, how to prepare them. In this chapter, we will learn how to make useful organic structures from alcohols. There are several reactions we can actually use alcohols as a reactant. One is dehydration to alkenes. The second is oxidation to aldehydes or ketones. Third, substitution to form an alkyl halide. Fourth, reduction to alkane. Fifth is esterification. Sixth, tosylation. And the last one is Williamson synthesis of ether. It's easier to see the equations of those reactions. The first one, starting with an alcohol, we can eliminate to give an alkene. We learned this reaction actually in the alkene chapter. And what we have seen in that chapter, that alcohol usually it has a very bad leaving group. So you're going to need to activate it. So what we use for the dehydration is H+ and heat. And that reaction actually went through E1 pathway. And that's why we say tertiary alcohol is faster than a secondary, faster than a primary. And that will be visited again in this chapter. Alcohol can also be oxidized to give a ketone, aldehydes, or acids. So level of oxidation goes from alcohol to aldehyde to carboxylic acid, or from a secondary alcohol to a ketone. So if I have a secondary alcohol to start with, I can oxidize it to a ketone. But if I have a primary alcohol, I may be able to oxidize it to an aldehyde or take it further to the next level, which is carboxylic acid. The third reaction is substitution. So OH is a bad leaving group. So we're going to have to activate it to be able to substitute it with another group, such as halides. So we'll see that reaction in the next part. Reduction, meaning taking off the OH totally. So we will see how we're going to do that. Esterification, so starting with an alcohol and making an ester out of it. So we're going to see that we're going to need H+ and the alcohol. And this reaction is actually given Fischer esterification name for the person who invented this reaction. And we will learn the mechanism of this reaction as well. Tosylation, so this is taking an alcohol and make it a better leaving group. So tosylate is one of the best leaving groups that actually we can have in a substrate for SN1 or SN2. So that's something we have learned in the nucleophilic substitution chapter. The last reaction is the Williamson ether synthesis. That's the best way how to make an ether. So we take an alcohol, we deprotonate it, we attack an alkyl X through an SN2, and it has to be a primary X or a methyl X. And then we're going to visit this reaction in the following part. And this, how we make ethers. Oxidation states. It's very important to keep in mind the level of oxidation. Well, let's start with defining oxidation versus reduction. Now, oxidation is usually referred to as loss of hydrogens, loss of electrons, or gain of oxygen atoms. That's how we define oxidation. While reduction is usually gain of hydrogens, gain of electrons, or loss of oxygen. So very similar to that will be the definition in organic chemistry. So when we have a substrate that gains oxygen atom or two oxygen atoms or halogens, usually that substrate is referred to as an oxidized substance. So loss of hydrogens also can be an indicator that you have an oxidation taking place. Opposite to that, gain of hydrogen or hydride, loss of oxygen or O2, and loss of halogens will be basically taking place in a reduction process. So if neither of the two pathways, features exist, then obviously you have neither reduction nor oxidation. And this is what's most important in this chapter, that we have the level of oxidation usually goes from an alkane to a primary alcohol. The next level of oxidation will be to get it to an aldehyde. The most oxidized level of alcohol is the carboxylic acid. So that's how the oxidation states usually are ranked. Then keep in mind that the primary alcohol is the only one that's going to be taken to a carboxylic acid. Why? Because the secondary alcohol will not be delivering a carboxylic acid. will be delivering a ketone instead. And the ketone in some reactions, you will be able actually to take it to an ester, but not a carboxylic acid. Here's the most important thing to keep in mind is if the alcohol is a tertiary alcohol, you cannot oxidize it, period. Whether you're trying to get an aldehyde or a ketone or an acid, tertiary alcohol is not a substrate to think about as an option. So that's important. And we will see the reason behind that. So there are several ways how we make alcohol oxidation be successful. It matters that we decide first what is the goal. Are we trying to make an aldehyde out of a primary alcohol, or are we trying to make a carboxylic acid out of an alcohol? Now, the secondary alcohol is determined that it doesn't go to that carboxylic acid. So you're going to see a lot of these methods that we use in the primary alcohol, they are also used in the secondary alcohol. So let's start with the most common method, that is for secondary alcohol, the green method, that is sodium hypochlorite, which is bleach, and acetic acid. So vinegar and bleach. So sodium hypochlorite and acetic acid, it's a common method that we use for secondary alcohol to take it to a ketone. And here's an example where you see a cyclohexanol being taken to a cyclohexanone. Usually it's a good yielding reaction. So this is considered to be a greener method compared to chromium methods. What is the chromium methods? Well, the most important method is the sodium dichromate in sulfuric acid. Now, the sodium dichromate in sulfuric acid usually delivers chromic acid in situ, meaning you are making chromic acid in the reaction, and that is your oxidizing agent. So the chromium, to be considered to be a toxic metal, obviously that's why people tend to use greener method that can deliver the same outcome if possible. Now, chromium, though, the chromic acid, it's a very strong oxidizing agent. So we will see that it can be generated using sodium dichromate, water and sulfuric acid, or chromium trioxide, water and sulfuric acid. In either of the two, whether you use the dichromate or you use the chromium trioxide, you will generate the oxidizing agent, that is chromic acid. And this is the structure of chromic acid. And that's important to keep in mind, that the chromic acid is the oxidizing agent in those two recipes. So the mechanism, which is, I'm going to give you just a short brief of what this reaction is about. The mechanism usually starts with the alcohol attacking the chromium reagent, whether it's coming from the dichromate or coming from the chromium trioxide, it doesn't matter. You will wait for the chromic acid to be formed before the alcohol can attack it. And once it attacks the chromium, what are you going to end up having? You're going to end up making actually this chromate ester, and this is an important intermediate to look at. Why? Because this hydrogen that's attached to the CO, which is this hydrogen right there, it is a must to be there for the water to abstract it, and that sigma bond will be the source of the pi bond that's going to be in the carbonyl moiety. And it's important to keep in mind that if I have a primary alcohol or a secondary alcohol, I will find that hydrogen. It will be there on the C attached to the OH. So there will be a chance for that hydrogen to be abstracted from that chromate ester to give you the aldehyde in the case of the primary alcohol, or the ketone in the case of the secondary alcohol. But in the case of tertiary alcohol, where you're going to have R prime, and R double prime, there's no hydrogen to abstract. So what's going to happen? The reaction will shut down, will not work. And that's why we say tertiary alcohol cannot be oxidized. Regardless what oxidizing agent we use, no matter how powerful it is, it doesn't go further. It does not give you aldehyde or ketone or a carboxylic acid. So here is an example. So you have a primary alcohol. Now the chromium in the chromic acid, it's a very strong oxidizing agent. Now it has to be sodium dichromate, sulfuric acid, or chromium trioxide, sulfuric acid, which will give me chromic acid to oxidize a primary alcohol to the carboxylic acid. Why am I saying that? Because we're going to see other reactions where I have chromium, part of the oxidizing agent, but is not strong enough. So it's very important to pay attention to the reagent where the chromium is part of. In this case, is the sodium dichromate. You could see here that the primary alcohol is being oxidized to a carboxylic acid. Now, keep in mind, there is an intermediate, of course. The intermediate is the aldehyde. So it doesn't go all the way to the carboxylic acid without going through the aldehyde. So you will oxidize the primary alcohol to the aldehyde first, and the strong oxidizing agent, since it's still around, it will take it further to the carboxylic acid. And as it's very clear that the oxidizing agent is too strong to stop at the aldehyde level. Now, what if I throw in chromium trioxide, sulfuric acid? Will I do the job of taking a primary alcohol to carboxylic acid? Yes, indeed. However, if you use other chromium reagents, such as PCC or PDC, PCC, pyridinium chlorochromate, or PDC, which is pyridinium dichromate. In those two reagents, and we see the PCC in front of us, what do we have here? We have a chromium trioxide, we have HCl, and we have pyridine. We mix all these together, we end up making a neutral oxidizing agent. This neutral oxidizing agent is not strong enough to take the primary alcohol all the way to the carboxylic acid. What does it do then? It only delivers the aldehyde out of the primary alcohol, and it delivers the ketone out of the secondary alcohol. So PCC, pyridinium chlorochromate, which is a mix of pyridine, HCl, and chromium trioxide. So it will form like a complex, as you see here. It's written as chromium trioxide dot pyridine dot HCl. The actual content of the reagent will be actually as written as pyridinium, as the counter cation of the chlorochromate, which is the anion part of the reagent. It's important that we remember that PCC or PDC can oxidize a primary alcohol or a secondary alcohol, but the secondary alcohol will not give you an aldehyde, rather will give you a ketone. The primary alcohol will be the one that's going to be taken to the aldehyde level. And you could see here examples. So here's a primary alcohol will be taken to an aldehyde. Here's an example of a primary alcohol that is heptanol. This heptanol, in presence of PCC, methylene chloride is just a solvent. I may not need to list it when I have a synthesis route to propose. I don't have to mention CH2Cl2. PCC will take the primary alcohol to the aldehyde level. And just to remind you, tertiary alcohol cannot be oxidized due to the fact that you have a hydrogen attached to the COH need to be there to be abstracted for the pi bond of the carbonyl to be formed. If I don't have this hydrogen, and that's the case in the tertiary alcohol, I cannot oxidize that carbon or that OH to the corresponding carbonyl. And this is the green method I was referring to, that sodium hypochlorite in presence of vinegar. That's usually the list of reagent that you need for this green method. It shows here that water can also be used instead of the vinegar, that alcohol, secondary alcohol, will be taken to the ketone. Now, to be on the safe side, vinegar to be used, which is acetic acid with the sodium hypochlorite, to make sure that we deliver a good yield of the carbonyl of that secondary alcohol. So let's review a little of what we have done so far. So we have chromic acid that we can generate using sodium dichromate, sulfuric acid, or chromium trioxide, sulfuric acid in presence of water. What are these two going to do? They're going to deliver chromic acid, which will oxidize a primary alcohol to the carboxylic acid, and will oxidize a secondary alcohol to the ketone. PCC, pyridinium chlorochromate, which is a mix of pyridine, chromium trioxide, and HCl, will oxidize the primary alcohol to the aldehyde and will oxidize the secondary alcohol to the ketone. The other method, which is the sodium hypochlorite and vinegar or acetic acid, these two together will oxidize a secondary alcohol to the to the ketone. Will it be used for a primary alcohol? No, it's not a common method to be used for a primary alcohol. It could be not strong enough to deliver the aldehyde. So that's why if the interest in that primary alcohol to deliver the carboxylic acid, then might as well just use the chromic acid, either of the two methods, dichromate or the chromium trioxide and sulfuric acid. But if the interest is in to form the aldehyde out of that primary alcohol, then you're going to have to use PCC, or there's another alternative, that is Swern oxidation. What's in the Swern oxidation? Swern oxidation is a mix of reagents. One is DMSO, dimethyl sulfoxide. That's one of the A product solvents that we learned in the nucleophilic substitution chapter. Second is auxiliary chloride, which is the COCl2. So you have two carbonyl attached to each other, and you have one Cl on one side of the carbonyl and one Cl on the other side of the carbonyl. So yeah, that's another reagent. The third is a base, that's a triethylamine. And the fourth is a solvent, which is methylene chloride. Now, do I have to mention the methylene chloride? No, you do not. You could be using another solvent and it will probably just be fine. But the Swern oxidation is known to be done using DMSO, auxiliary chloride, and triethylamine. What does it do? It takes a primary alcohol to the aldehyde, and it could also oxidize a secondary alcohol to the ketone. So is this an alternative to do instead of the PCC? Yes, it is. In fact, it's better when it comes to the toxicity level of the reagents that we're using, because in the PCC we have chromium. In the Swern oxidation, we don't. We rather have actually side products that all are gaseous. So HCl and CO usually are gaseous. Dimethyl sulfide, that's another a green reagent that is safe actually to handle, and compared to the chromium, which is obviously a toxic reagent. Another method that can do the same job as the Swern or the PCC is the dis-Martin periodinane. Dis-Martin periodinane, which is basically this triacetate iodine containing reagent. It takes a primary alcohol to the aldehyde and could also take a secondary alcohol to the ketone. So, so you have the PCC, PDC, DMP, or the dis-Martin periodinane, and Swern oxidation. They all do the same exact job. Obviously, the best method out of those is the Swern oxidation when it comes to considering the environment-friendly reagent nature of it. That will be the choice. Here's a question is asking to propose a method to go from cyclopentanol to cyclopentanone. The fact it's a secondary alcohol, the cheapest way to do it is to use the green method, that is sodium hypochlorite and vinegar, which is acetic acid. So that will take it to the ketone structure. Here's another one. So we have a primary alcohol. The interest is to make an aldehyde. So we're going to have to use PCC, Swern oxidation, or DMP, dis-Martin periodinane, or you could also use the NaOCl tempo. That could be an option, but this will be an expensive route to do it. So I would pick one of the three, preferably the Swern. Second will be the DMP, and PCC will also be another option to take a primary alcohol to the aldehyde. Oxidation also exists in biological cycles. The enzyme that catalyzes the oxidation process is called alcohol dehydrogenase. So it oxidizes the alcohol to the aldehyde, oxidizes the aldehyde to the carboxylic acid. And the oxidizing agent is the NAD+, which is the nicotinamide adenine dinucleotide. This oxidizing agent, in presence of the enzyme, will take a primary alcohol or a secondary alcohol to the next level, which is the carbonyl structure. So you could see here an example that if I have ethanol in my body, what would I expect the process to be for the body to excrete it? Well, what's going to happen? It will be oxidized to the acetaldehyde. The acetaldehyde will be converted transformed to the acetic acid using the NAD+ and alcohol dehydrogenase. And obviously, vinegar will be a safe structure then to be basically a normal metabolite, and that will be the way how our body takes care of ethanol toxicity, and that's important to keep in mind. Now, of course, methanol, it's a bad thing to have in terms of being exposed to it. Why? Because methanol gets converted to methanol, and methanol will be converted to methanoic acid. So that will be a substance that's not easy for our body to excrete it on our own. So that's why it will be required to have a medical intervention at that point, compared to ethanol, which is safer for our body to actually excrete it. Of course, to some extent of toxicity, doesn't mean that a high dose of ethanol is okay. This is another example. So we have the ethylene glycol, can also be oxidized to the oxaldehyde and then taken further to the oxalic acid. So the same process that, as I mentioned previously, that those substrates usually require an enzyme and an oxidizing agent. And the oxidizing agent usually is the NAD+, and the enzyme will be the alcohol dehydrogenase. What we're gonna see next is reactions of alcohols as electrophiles and nucleophiles. Now, just to remind you, we've seen the alcohol function group in the nucleophilic substitution chapter listed as a weak nucleophile. And we also seen it in that chapter as it's a bad electrophile, the fact that OH is a bad leaving group. So we are required actually to activate the OH to be a good nucleophile and activate the OH to be a strong electrophile. So in order for us to make it a good nucleophile, then obviously I'm going to have to deprotonate that hydrogen from the alcohol to make an alkoxide. And that's what we've seen in the nucleophilic substitution chapter. All alkoxides are strong nucleophiles. So that's important. But in either case, the alcohol usually on its own, it will be a weak nucleophile. If it reacts with an electrophile, it depends on what electrophile we're dealing with. It will go through a substitution or elimination, depending on what electrophile we're reacting it with. So to make it a good nucleophile, we will have to deprotonate the hydrogen of that alcohol. I can do this using sodium. I can do this using sodium hydride. I can do this using lithium. Any of these methods, preferably the sodium hydride, because the outcome will be hydrogen. So it's easy to actually deal with pushing the reaction to the right. So having the hydrogen being deprotonated is going to give you an alkoxide. Now that alkoxide, it will be a much stronger nucleophile, and that's why the reaction will be favored. The nucleophilic substitution will be favored if we transfer the alcohol to the corresponding alkoxide, and that will basically deliver the SN1 or the SN2, depending on what substrate I am dealing with. Alcohol as an electrophile. It's a bad electrophile due to the fact that the OH is a bad leaving group. So what do? We activate the OH to make it a better leaving group. How? We reacted, as an example, with toluene sulfonic acid. What is this structure? It has a toluene group attached to a sulfonic acid moiety. This is the source of tosylate. So when this alcohol sees a tosyl paratoluene sulfonic acid, the oxygen eventually will be attached to the sulfur, generating water as a side product. So we're going to have a tosylate molecule. We've seen tosylate as a group in the nucleophilic substitution chapter as the best leaving group compared to mesylate, which can be actually done the same way. Methane sulfonic acid reacting with alcohol will give me the mesylate. Better than an iodide, better than a bromide, better than a chloride, which are better than fluoride and alcohol and amines and ether. So this is important to keep in mind, that alcohol is a bad leaving group. So if I want to substitute an OH, I'm going to have to go through another step first, which is making a better leaving group, make a tosylate out of it, as an example. And once we have that tosylate, what it can do next will be basically the the nucleophile will attack that carbon that has a tosylate, and that will end up making the substitution outcome. Or if the interest is to make an elimination product, then obviously I will be using a base to abstract that alpha carbon hydrogen to make an alkene, and that will be the alkene product out of the elimination of tosylate. So we can see here that I can make alcohol a better nucleophile by deprotonating the OH using sodium, using lithium, using sodium hydride. I can also push that alcohol to be a better leaving group using a toluene sulfonic acid. Para-toluene sulfonic acid will make the OTS, the tosylate. If I'm interested to make the mesylate, all I need to do is to use methane sulfonic acid, and that will give me the mesylate. Either of the two, tosylate or mesylate structures, can be used in SN1, SN2, E1, or E2, depending on what alkyl classification I have. So we could see here that tosylate can be used in SN2. So I have a secondary alcohol that's been transformed to a tosylate, and this carbon happened to be a stereo-defined one. So that's an S-labeled structure carbon. So we could see here clearly that the SN2 delivers the inversion of configuration. So that's how the strong leaving group I have. It pushes the reaction to go through SN2, not an SN1. So that's very important to keep in mind. And as I say, the better leaving group is usually defined as the structure to be a weak base. The weaker it is as a base, the better it is as a leaving group. So always think of that leaving group as an anion. Is that anion a weak base? Because if it is, then we have a very good leaving group. And why is it a weak base? Because of the stabilization through resonance. So we can see here that the O- will be delocalized to actually give you the second structure with also an O-, and that will also be stabilized with a third. So that's important to keep in mind why the tosylate is a good leaving group. It's because of the stabilization of the conjugate base that makes that OTS a weak base, therefore a good leaving group. You can see here the diversity in the reactions of tosylates. What else we can make out of those? So we could see here that if I have a tosylate structure with a hydroxide, I can make an alcohol. If I have a tosylate with a cyanide, that's another SN2 that will give me a nitrile. Tosylate in presence of halide, that will go through also substitution to give me an alkyl halide. Tosylate in presence of alkoxide, that will give me an ether. Tosylate in presence of ammonia or an amine will give me an ammonium or an amine salt. Tosylate in presence of lithium aluminum hydride, which is the source of H-. What does it do? Reduction. It takes off the OTS totally, and it substituted with an H-. So that's important to keep in mind, that this is the way how we make reduction of alcohols, actually. To take it to the tosylate and take the tosylate, treat it with lithium aluminum hydride, and that will give me the alkane strength. Can I do this using sodium borohydride? Can I do this using hydrogenation? No, you cannot. You have to use a strong reducing agent that's a lithium aluminum hydride. So here's some examples. So if my interest is to go from the alcohol, cyclopentanol, all the way to the cyclopentane, what is that? That's reduction. Well, there is one way, which is elimination, E1, to give me the alkene, and then reduce the alkene using hydrogenation condition, catalytic hydrogenation, which is H2 and over platinum or nickel or palladium. That will give me the cycloalkane. There is another way that's even better in terms of yield. Take the alcohol, treat it with para-toluene sulfonic acid, or even more reactive, the tosyl chloride. Tosyl chloride, the only difference between para-toluene sulfonic acid and the tosyl chloride is just the leaving group. In the para-toluene sulfonic acid, you have an OH. In the tosyl chloride, which is even better, you have a Cl. So this will be a faster reaction. However, required to have pyridine. Why? Because I'm going to end up making HCl out of this step. So you want to make sure that the HCl is being quenched. neutralized, and that's why we have the pyridine. Pyridine has nothing to do with formation of the tosylate, has to do with taking care of the HCl resulting from the reaction. So if I have the alcohol reacting with tosyl chloride, I will be making tosylate. Treating that with lithium aluminum hydride will deliver the cyclohexane. So that's another alternative for those who don't like to do elimination followed by a harsh condition that's acid catalyzed, or the acid catalyzed elimination followed by hydrogenation. I could do alcohol, the tosylate, take the tosylate, expose it to lithium aluminum hydride, and that will deliver the RH at the end. What we're going to see next, additional reactions of alcohols, delivering esters, delivering other functional groups such as alkyl halides. We will see diols, oxidation, and some other reactions as well.